The first thing you need to do is make the keyboard frame itself. I'm using a laser cutter for this with a design that I made on Inkscape because it's just way easier for this kind of repetitive work. The first layer is just a back. The second layer, turns out you don't really need this. And then the next layer actually holds all the buttons in, it presses them from behind and provides channels for the wiring. The top layer actually holds the buttons in place and has all the key letters printed on it as well. So once you've got that made, you need to flip it over and insert a whole bunch of buttons. These you'll do with the legs sticking out either side. So the top row of legs on the button is one contact and the bottom row of legs is the other contact. What you need to do is to make sure it all fits together nicely, then glue it together, and then you can look at wiring. So I've inserted some pins for the Arduino headers here, and we're basically going to wire up rows, which we're doing now, and then columns, which go up one side to one of the Arduino pins, and then down the other side immediately opposite that black line that I drew, which is 8 buttons in from either side. This is a really time-consuming process, so I'm not really showing it all, and I've sped up the stuff that I am showing. But the idea is that at the end of this you will have a what is basically an 8x8 grid of buttons available to you. Okay, so we've now got our keyboard finished. I've put the back panel on here, just held on with some bolts, and I have soldered on some more pin strip at an angle, which will hold the Pixel board at an angle that's much easier to see. You could have just used some longer pin strip and bent it, but I didn't have any, so I just whacked this on. So you put the Pixel board on. In order to get enough I/O pins, we've actually had to mount it upside down. But this means that we've got pins D0, D1, D2, D3 all the way up, and then SDA and SCL here. So these are A4 and A5, but basically every single pin on this pin strip is now used for the keyboard. That's 16 IOs in total, and I've got them listed up here. So if you want to see what this works like, we can just use the Keypad module. This handles all the scanning of this keypad in such a way that it doesn't actually use any power when it's just sitting here waiting for keys to be pressed. So it's a really nice way to make battery powered devices. It's going to call handle key press whenever a button is pressed, and it basically decodes the X and Y value. Now our keys are arranged on a 8x8 grid, so top half of the 8x8 grid is the left hand keys, bottom half is the right hand keys. If I upload this code and then I press the buttons, hopefully we'll see that, so this is the second pin in, so 1 on the top row, 0. If you work the way along, so it counts up, go to the next row, it's now counting from 0 again, but it's actually on row 4. Same here, so if we go down this way, it counts up 0, 1, 2, 3, 4, 5, 6, 7. So all we have to do now is decode this. Now, to save going through a lot of code, I've actually done something like this before. This is using a whole bundle of wires and some membrane keypads. The bonus of this one is that you can just use proto board, you don't have to do any soldering, but it doesn't look as nice. So we're just going to copy this stuff, not the key row and key column, because they're slightly different on this one. But you can see that we've got these key maps now. So the key maps basically match exactly what's written on the keyboard. So for instance, if you were making a keyboard for another country, this one's based on the British keyboard layout. You might want to change what some of these are. So what we've got the normal keys in here. We've got key code 1, which we handle separately down here. This is actually the shift key. And then anything starting with X8, so this is a key code that is 128 and above, is looked up in this array. And this array contains keys that are basically escape characters. They're actually a sequence of key presses. And this is just what a VT100 terminal, which is what what is implemented by basically the left-hand side of the Espruino IDE expects to see for up arrow, down arrow, and things like that. So yeah, when you press the Shift key, it will display something in this corner here. And otherwise the handling is pretty simple. It's turning that 8x8 grid into a 16x4 grid. It handles the Shift key. It figures out whether, if the Shift key is pressed, whether to use the upper case key map or the lower case key map. And then it calls terminal.inject with the key, which is basically, it's simulating a user key press. And that's basically it. So the only other thing to watch out for is, as you can see from this, the screen's actually upside down because we've got the pixel upside down. So we need to rotate it. We can do this by writing a function called onInit, which will be called when the board starts up. Just so that we can demo it properly, we'll make sure we call it when we upload. So we can do g.setRotation, which will the value is the number of 90 degrees to turn it. So 290 degrees will turn it completely upside down. Let's clear the screen because it'll have the wrong stuff on it, and write it, and then we'll do terminal.println, and we'll just say hello or something, just so that the screen is not completely blank. Finally, we might want to adjust the contrast here, because it's not quite right when it's viewed with this camera and the lighting we've got. And then we might want to turn the backlight on. And that's it. So if I now upload this, see, it'll upload, and now it's done. It says hello. So we're not actually seeing anything at the moment. And we're not seeing anything because the console is still on Bluetooth, which is, it's on the IDE, so we can interact with it. So to manually set it back, we could disconnect via Bluetooth. In fact, let's just do that. It's easier. Disconnect from Bluetooth. Hopefully it's going to say it's come from Bluetooth and it's got the prompt. So we can now type some things. We can do some maths. We can say 1, 2, plus 3, 4. So to do plus is above equals. Press the Shift key. Press plus 3, 4. Now the only thing to watch out for here is that the keypad can't detect when two keys are pressed at the same time. So we've had to make Shift toggle rather than act like a normal Shift key, which you'd hold down and press. So yeah, if I hit enter, we'll see the result. In fact, we can even do things like drawing on the screen. So if I say I don't want set draw rect, and you can use tab complete as well, but I won't show that. Okay, so we'll do it at 60 by 40 by 80 by 60, which should put a square quite near the bottom. Okay, and there we go, we've got the square. In fact, we can, when we press enter, the square will scroll up with all the other text. So if I scroll up and then I do it again, we'll get another square there as well. So you can actually do a whole bunch of different stuff with this. You can set intervals to run in the background, for instance. You can control these I/O pins that are at the top. So these are all the analog capable I/Os. 2 of them are still used for the SDA and SEL pins, but that leaves 4 available I/Os that you can control, just using .set and .reset and .write and things like that. So for instance, if I wanted to turn the backlight off, I could do LED .reset, and it's off. And I can go back and do LED.set to turn it back on. So I just spelled that slightly wrong. Okay, so currently all of this is in RAM. To save it to read only memory, you can just type save. So now if you unplug the power and plug it back on, it will always come back up in this state. The only thing to watch out for is that if you type reset, it will actually remove all of the code from this, including the code that you've just written. So to work around that, in the Web IDE, you can go to Communications, Save on Send, and choose Directive Flash, Execute Code at Boot, even after a call to reset. So this will ensure that your code always stays running, even if the user were to try and reset everything, which makes it into a fully functional little computer. I say you can do the IOs, you can use Bluetooth on it, you can use regular expressions, JavaScript ES6, like arrow functions, template literals, all kinds of fun stuff, including classes, all on this tiny little battery-powered device. Now, it's amazingly low power as well, so without the backlight on, this is drawing about 300 microamps. So realistically, if you put a watch battery in that, a TO32 watch battery, it would last for around about 20 days. If you actually put a small solar cell and battery on here, it would basically just stay running forever. And that's it. I will put all this information online, including the XF files for cutting this keyboard out. Although I'm kind of aware that not everyone has access to a laser cutter that can do this kind of thing. So if you're interested in getting hold of one of these, please let me know in the comments, because it's probably something that I can get laser cut and offer for sale. Thanks for watching. If you like this sort of thing, please subscribe, because I'm going to be trying to produce a whole load more videos of fun things to do with microcontrollers. Also, there are a bunch of videos already on the Espruino channel on YouTube, and there are a whole load of projects on the Espruino.com website, over 100 now, to do with Espruino boards like this Pixl.js. Okay, thanks for watching.